I'm giving this presentation because I have a concern that there are hundreds, if not thousands, of buildings being designed and built each year that should have smoke dampers protecting the air handling systems, but don't. In this presentation, I will explain why I believe smoke dampers are required for most air handling systems. This presentation is the result of a proposal for change that was submitted for NCC 2022 called Adequate Protection Against Smoke Spread by Air Handling Systems. Before we get into the details of this presentation, I want to put some limitations on what the presentation will cover. What I will talk about is general purpose air handling systems. And where we talk about fire mode operation, it is a shutdown system provided with dampers. I will not talk about smoke control systems, and I will also not talk about special hazards, which are covered by clause E2.3 of the BCA. I'll start off by giving you an overview of my presentation. First, I will talk about fire dampers and why fire dampers cannot necessarily protect against smoke spread through the air handling systems. I'll get into the changing construction practices around building envelope airtightness and how that affects the risk of smoke spread in buildings. That is followed by a discussion around what is acceptable levels of smoke spread between fire compartments. Then I will relay the results of a technical analysis that was done in the proposal for change I submitted last year, and that really quantifies the amount of smoke that can spread between fire compartments. And from that, I'll draw some conclusions and propose a new framework for deemed to satisfy compliance around smoke dampers. There are a few key things that I want you to take away from my presentation today. Firstly, what I will say around smoke damper requirements and the interpretation of the deemed to satisfy provisions may conflict with your own interpretations and how you've practiced. It's not my intention to place any blame. The DTS provisions around smoke dampers are very complex, and consequently it's no wonder that building practitioners differ in their interpretations. In my opinion, the deemed to satisfy provisions that govern smoke damper requirements are too complex and need to be amended to be made more clear. Secondly, I'm going to show you that fire dampers cannot replace the need for smoke dampers. Each type of damper serves its own purpose. Finally, the way we build buildings is changing. Increased air tightness of building envelopes and more prevalent internal sealing of compartments, for example, with the use of smoke seals to doors, will have a dramatic effect on the risk of smoke spread in our buildings. Often I hear people say, why do I need smoke dampers when I have fire dampers in my air handling system? Well, to answer that question, we need to understand how a fire damper works. Fire dampers, as the name suggests, are there to mitigate fire spread. A fire damper that achieves a fire resistance level in terms of integrity is there to prevent hot smoke to transfer between two fire compartments. A smoke damper, on the other hand, is designed to prevent the spread of cold and medium temperature smoke. And by medium temperature, I mean temperatures up to 200 degrees. To understand the role of smoke dampers in fire protection of air handling systems, we need to understand the operation of fire dampers. In Australia, fire dampers can be mechanical, for example, a curtain damper activated by a fusible link, or an intumescent damper, which is activated by the swelling material in the damper itself that closes the air path, or a motorized fire damper, which is driven closed by an actuator. Mechanical and intumescent dampers are the most common due to their low cost. Let's have a look when fire dampers activate during a fire. In this example, we assume that the fire damper is an intumescent damper. Intumescent materials sometimes require temperatures well in excess of 200 degrees to activate. On this graph, we've got two different time temperature curves shown. One is the standard ISO 834 time temperature curve used for testing of fire resistance levels in many countries around the world, which includes Australia. The other curve is a natural fire time temperature curve, which more accurately represents a fire that reaches flashover, turns into a fully developed fire, and then decays as the fuel in the compartment is consumed. Because of the rapid heating of a standard fire curve, the temperature is sufficient to activate the damper almost immediately. Therefore, if one assumed that the standard fire curve was representative of a natural fire, one would expect the fire damper to activation to occur very rapidly. However, if we subjected the same fire damper to a natural fire curve, then there will be a significant time period before the room exceeds 200 degrees Celsius, which is shown here by the red arrows. After the room reaches 200 degrees, we can assume that the fire damper closes. But in the time that the fire grows and the temperature is below 200 degrees, the fire damper remains open and smoke can pass through. During this time, smoke can spread through the air handling system. Smoke spread through an air handling system is treated as a flow. Fluid flow, which applies to air and smoke mixtures, always flows from higher pressure to lower pressure. Therefore, if two fire compartments are connected by an air handling system ductwork and there is a pressure difference between the two compartments, flow will occur by the ductwork from the higher pressure compartment to the lower pressure compartment. If there's no pressure difference, there's also consequently no flow and therefore no smoke spread. To understand the flow of smoke or smoke spread by air handling systems, we need to understand what happens to a compartment in the early stages of a fire. For the purposes of this discussion, we assume that the compartment is sealed. By that I mean that any windows or doors are assumed to be in their closed position and that there are no major permanent openings to the outside. A fire releases heat into the compartment. That heat leads to a volumetric expansion of the gases. However, because the expansion of those gases is constricted by the compartment, that instead leads to a pressurization, which I refer to as the fire-induced pressure. Because of that pressurization, the fire-affected compartment is at a higher pressure than the other compartments surrounding it, and smoke spread can occur due to the pressure differential generated. It can be shown that the pressure induced by a fire in a compartment is proportional to the square of the rate of temperature increase. What that means is that the faster the temperature increases in the compartment at any given time, the greater the pressure. To make things less abstract, let's take a look at the natural fire curve we used earlier. The rate of temperature increase at any given time can be visually expressed by the tangent line. In the early stages of the fire, the rate at which the temperature increases is greater than zero, and this creates an overpressure in the compartments. When the temperature reaches its peak, in this case around 1000 degrees, the rate of temperature increase is zero. Consequently, there's no pressurization from the thermal expansion of gases. In the decay phase, when the temperature drops, this leads to an underpressure. Pressure that can be generated by fire is also proportional to the leakage from a compartment. The larger the openings, the larger the leakage, and the lower the pressurization. Current trends in building include more energy efficient buildings. One key component in such buildings is limiting infiltration of outside air by using more airtight building envelopes. NCC 2019 saw the introduction of a verification method for building envelope performance. And we also have voluntary standards such as passive house standard that are becoming more prevalent in Australia. Internally, we're also using more acoustically sealed compartments, and that includes, for example, acoustic and smoke seals to doors. These trends lead to smaller and smaller leakages from our compartments. To put things into perspective, this graph shows the minimum and maximum level of airtightness of 80 non-domestic buildings in Australia from a 2018 study. The maximum amount is about 18 and the minimum is about E2.2. In this graph, we've introduced a blue line that shows a maximum allowed leakage via the building envelope for commercial buildings that seek to demonstrate compliance with verification method JV4 for NCC 2019. The red line shows an approximation of the allowed leakage via the building envelope to meet the passive house standard. What I'm trying to convey here is that older buildings have traditionally been much more leaky than the buildings that are being built now and into the future. With the improvements in building envelope sealing, what kind of fire-induced pressures are we talking about? To answer that question, we can draw on the results from a 2019 study I did on the peak fire-induced pressures that can be generated in a fire compartment of varying levels of building envelope sealing and internal sealing using smoke seals to doors. The results show that the older building stock was typically associated with pressures of 100 pascals or less. This level of fire-induced pressurization leads to minimal or no smoke spread through air handling systems. However, for modern or passive house levels of building envelope airtightness, the theoretical fire-induced pressure generated commonly exceeded 1500 pascals. Such fire-induced pressures will cause smoke spread through air handling systems if not managed. That means that in the growth phase of a fire, the pressurization from that fire in a modern building will be much greater than that of an older building, despite the time temperature curve being identical. So what are the consequences of these increased levels of pressurization from a fire in modern buildings? To give you an example, I want you to consider a building that has a mechanical supply and a mechanical exhaust system serving multiple fire compartments. And you can think of these fire compartments as hotel rooms. The mechanical supply and exhaust is each 50 liters per second to each room, and the branch pressure loss from a hotel room to a main duct for both the supply and exhaust system is assumed to be 50 pascals. For our old building stock, where we can get a maximum of 100 pascals of pressure, the flow of smoke out from that compartment will be a maximum of 136 liters per second. However, in our modern building that can reach pressures of 1500 pascals, the flow of smoke is quadrupled and reaches 548 liters per second in this example. This has a massive impact on the risk of smoke spread. Because our older building stock has been relatively leaky, high levels of fire-induced pressurization and smoke spread through air handling systems as a result of that pressurization is not a problem of the past. The problem is an emerging hazard as the result of the improved sealing of our buildings that we're currently building and that will exist in the future. It is important that we building practitioners are aware of this hazard so that we can adequately manage it in building designs. For those of you who are not convinced, I want to show you a video from a Finnish study. In this experiment, the firefighters light a polyurethane mattress inside the closet of an apartment. In the bottom left, you can see a graph of the fire-induced pressure that is measured inside the compartment. At about 1600 pascals of lower pressure, the window frame gives in and is pushed out of the wall from the pressure. Okay, so we've so far shown that fire dampers cannot protect against smoke spread in the early stages of a fire. We've also seen that in this stage of the fire, pressures can be high, especially in modern buildings. Now I'd like to quickly review the deemed to satisfy provisions that apply to smoke dampers. In my opinion, these are E2.2b, which are the general provisions for air handling systems. There's also E2.2c, which applies to miscellaneous systems. I won't talk about kitchen exhaust systems, which are also covered by that clause. Finally, there's E2.3, which talks about special hazards. Again, that will not be covered by this talk. Sometimes when I talk to building practitioners, they tell me that E2.2b is not applicable to their miscellaneous system, and instead only E2.2c applies. I disagree with this because the BCA is very explicit about where different clauses are mutually exclusive, and it uses the word or to show this. There's no or between E2.2b and E2.2c in the BCA. Therefore, in my opinion, both of these clauses apply to a miscellaneous system. E2.2b is a deemed to satisfy clause that I spent a lot of time reading. It is very complex if you ask me, more so than necessary. It includes a number of terms such as air handling system and smoke hazard management system that are not defined in the BCA. That just makes things worse. Your first job with E2.2b is to determine if it applies at all. Say you've determined that the system is an air handling system and that it's not a smoke hazard management system. At that point, if the system recycles air between fire compartments, then E2.2b applies. However, if your system does not recycle air between different fire compartments, but the system may unduly contribute to the spread of smoke from one fire compartment to another fire compartment, then E2.2b also applies. If you ask me, the really tricky part of E2.2b is to determine what is unduly contribution of smoke spread between fire compartments by an air handling system. That's what I'll focus on in the next few slides. What unduly contribution means is a judgment call by the building practitioners. In this case, the fire safety engineer and the building surveyor or certifier, in my opinion. I don't have the answer to what unduly contribution is, but I'll share a few of my findings here. That includes what is discussed in the guide to the BCA, also a survey among building practitioners, and what can be found in other regulatory frameworks. The guide to the BCA is actually quite strict and suggests that the fire mode operation of air handling systems should not contribute to the spread of smoke between fire compartments. To me, this reads as no smoke spread is permitted at all. As part of the proposal for change that I developed for NCC 2022, a survey was sent out to building practitioners around Australia. 122 people responded, and 115 of them had more than 5 years of experience of practicing. The survey asked the people to answer the question, what does operate in a manner that may unduly contribute to the spread of smoke from one fire compartment to another fire compartment mean? 38% responded that no smoke spread is allowed. Another 38% stated that it was okay to spread between 1 and 5% of the receiving fire compartment's volume. Only 1% stated that smoke spread was allowed to be more than 5% of the receiving fire compartment's volume. So most building practitioners suggested that there was no or very little smoke spread allowed between fire compartments. The only regulatory framework for fire safety engineering that quantifies acceptable smoke spread between fire compartments is Sweden's BBRAD. In that framework, the acceptable limits of smoke spread is 1% of the receiving fire compartment's volume for any use that includes sleeping occupants. For other uses that have non-sleeping occupants, the acceptable level of smoke spread is 5% of the receiving fire compartment's volume. To make my case for why smoke dampers are required in general for air handling systems, in the proposal for change I submitted last year, I modeled how much smoke would spread between fire compartments through a few air handling system designs that were common to Australia. All of these air handling system designs would be classified as miscellaneous systems and also what's referred to as minor systems. The building envelope airtightness was varied in the study and was either selected as the NCC 2019 verification method requirements for new apartments or the level that is required to achieve a Green Star credit. None of these designs were provided with smoke dampers. and the effects of sprinklers was analyzed as both cases where successful operation and failure were included. This slide shows one of the common system designs that were analyzed as part of my proposal for change. It has a centralized outside air provided to the fire compartments. For example, you can imagine these as hotel rooms via ductwork in the corridor. We also have a few shared toilet exhaust fans providing exhaust. This graph shows the results in terms of smoke spread for the 46 scenarios analyzed as part of that proposal for change. The volume of smoke spread is expressed as a percentage of the receiving fire compartment's volume. The minimum amount of smoke spread was 1.2% and the maximum was 82.3%. I want to stress that smoke spread occurred for all system designs. I also want to point out that some of the cases included successful sprinkler operation, and that shows that successful sprinkler operation does not necessarily prevent large amounts of smoke to spread through air handling systems. With reference to both the guide to the BCA as well as the overseas acceptance criteria that was discussed earlier, all of these designs should be provided with smoke dampers. Based on the survey among building practitioners, it would also seem that most building practitioners would prescribe smoke dampers to these designs if they were told how much smoke would otherwise spread through the air handling system. The conclusion I drew from this is that smoke dampers should be assumed to be required for any general purpose air handling system in modern building designs. Based on this conclusion, I developed a new proposal to amend clause E2.2b. The baseline assumption in this new clause is that smoke dampers are required except for openings in external walls. The new clause also defines what systems are exempt from compliance with E2.2b through the term air handling system for smoke control, and I'll show on the next slide exactly what those systems are. E2.2b also includes a number of other clarifications to make it easy to interpret and to apply. In my proposal, I've also suggested to remove miscellaneous systems from E2.2c. In my opinion, the concessions granted to minor miscellaneous systems in Australian Standard 1668 Part 1 is a life safety risk to occupants in modern buildings. Those types of systems provide an adequate level of safety for our older building stock, but should be phased out as a compliance pathway for new buildings, in my opinion. Finally, I just want to show what systems were referred to as air handling systems for smoke control, which were exempt from the new proposed clause E2.2b. These are, for example, stair pressurization systems, zone smoke control systems, or smoke exhaust systems. That covers my presentation for today. However, for those of you who are interested in exploring this topic further, I have a few resources that I can share with you. Firstly, the proposal for change that I developed last year, which I've drawn upon today for this presentation, contains a large volume of information on the topic. Secondly, and more in general around the effects of compartment pressurization and risk of smoke spread from fire as a result of more airtight building envelopes. There's a paper from 2019 that I did for Interflam that talks about this. Finally, there is a number of research reports and peer-reviewed journal articles from Aalto University in Finland that are very, very good, that I highly recommend. That's it for me. Thank you for listening. I really hope that you've learned something today and that you thought that this time spent listening to me was valuable. If you have any comments or questions, feel free to reach out to me.